So we're live. I wrote down here, hey, the first unit, chemistry. We're going to be looking at chemical reactions and radioactivity. It's chapters 4 to 7 in your handy-dandy little textbook. Make sure you keep this textbook sign-up sheet passed around, and make sure you keep the hole puncher passed around. What are we going to learn about? Well, we'll learn about how and why compounds form, or atomic structure. We'll learn about ionic and covalent bonding. We're going to learn how and why chemical reactions occur. We're going to learn the different types of compounds, acids, bases, organic compounds, etc. And then the cool one, although the tricky one, we're going to be learning about radioactivity and radioactive decay. Again, it bears repeating, if you have a cheap, crappy old calculator, you want to bring it to this class, have a nice scientific one for your math class, but you will want to have something that can add and subtract three-digit numbers for the chemistry unit, and you'll be wanting to multiply and divide with decimals for the physics unit, so it's worth having a calculator. This is the hint. It's very important to stay up to date. I did this rant the other day, but I'll say it again. If you are stuck, rewatch the lesson at home if you need to. Come in for help. Do not fall 5 or 6 lessons behind. And I got to be honest, this is the toughest unit, based on prior experience. One of the cooler ones, though. So let's jump on in. Oh, you will also need a scientific calculator for parts of this unit. Sorry, a calculator, not a scientific calculator. So suggestion, if you have a cheap free calculator at home, bring that one to science, bring your fancier one to math. No, you cannot use your smartphone as a calculator. Why not? Could search answers, could take a picture of the test and pass it on to your friends. Could text your friends for answers. If they wrote an app, and I've asked people to do this, if they would write an app that would allow me to type in a password that would disable your Wi-Fi and your camera for 2 hours, then I'd let you use your phones, but they haven't. And honestly, if somebody wrote that app, a kid would find a hack around anyways. So, sorry, it's got to be a standard calculator. Okay? So, now we begin. I wrote down here, now this is in theory review from Science 9, list the 3 subatomic particles and their respective charges. So when you look at an atom, when you zoom in on the atom, we learned last year that there are 3 what we called subatomic, smaller than the atom, particles. Who remembers what they are? Proton, neutron, and electron. You know what? I'm going to be really, really clever, and I'm going to go proton, and mine does tables in my notes automatically. Neutron, electron, and what's the charge on a proton? Positive. What's the charge on a neutron? Neutral. I'll put a 0 there, or you can write neutral. And the charge on an electron? Negative. That there explains almost everything in the universe. You add a couple of more rules and everything falls out of there. You want to explain almost anything that happens? Protons repel each other, electrons repel each other, protons are attracted to electrons. There's some other funky stuff going on inside the nucleus, and there's your universe. Which one is the lightest? Sorry? Which one is the heaviest? Going to give you a hint. It's a tie, sort of. It's both the proton and the neutron. They weigh almost identically, in such that we're going to treat them good reach across? Thank you. We're going to treat them as though they have identical mass. I think somewhere on like the 10th or 12th decimal place they differ, but shh. We're not going to say anything. We don't care. Protons are heavy. Electrons are light. Which one takes up the most space in the atom? Ooh, this one's a bit more obscure. Yeah. Actually, it turns out the electrons do. We actually think that electrons behave sort of like clouds. Electrons, Sean, are some of the weirdest things in the universe. They're both particles like dots. You can treat them that way mathematically. They're also waves like radio waves. They're also clouds. And every one of those models works to predict some stuff and doesn't predict other stuff. So we talk about the particle wave theory of matter, which kind of says they're both things at once through some kind of quantum witchcraft or quantum science. So takes up the most space. The nucleus that holds the neutrons and the protons is very, 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 very what? Small. Okay? In fact, most of the atom is empty space, but the electrons take up more than the neutrons and the protons. I wrote down here, draw a diagram of an atom showing where these particles are. I can't draw. Usually on a computer, I'll use graphics, but just to show you how bad, I'll draw this time. So here's our diagram of an atom. Traditionally, we do something like this. Yep. That's what we call the nucleus. Which charges are in the nucleus? Sorry, which subatomic particles are in the nucleus? So symbol for proton, P+. P for proton, and we put a plus sign on it, Maleva, to remind ourselves positive, and that kind of works. Protons are positive, protons are positive. How will I remember that protons are positive? If I was a good teacher, I'm sure I'd come up with some way for you to remember that protons are positive, but I got nothing. And then our symbol for neutron is an N with a little 0. Looking at that symbol, can you think of a way that you can remember that neutrons have no charge? Looking at that symbol, can you think of a way that you might be able to remember that neutrons have no charge? You know what? Again, if I was a good teacher, I'd probably be able to give you some easy way to remember that neutrons have no charge, but I got nothing for you. And then we have on the outside, we have electrons. This is controversial, Jared, what I just drew, and technically wrong, because they don't do lovely little circular orbits or shells. All of the shells have different very, very funky shapes, and in fact, they're very, very complicated. So that's why we're always careful to say what we're showing you is a model of an atom, nowhere near close to the real thing. Also, this is totally wrong to scale. If this was actually the size of the nucleus, the first electron would be somewhere around the moon if I was trying to draw this on a piece of paper. So understand, Donna, this is for us to wrap our brain around, but the size, the smallness of it is easily beyond our ability to wrap our brain around. And that's why I went on the rant and well, it's very, 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 really infinity small. How small? Don't even try. I'll show you a video that's going to try and break it down for you somewhat. Tough. Put your pencils down. Here is the video. Now some definitions and blanks to fill in. If I give you something under definitions, probably, Trent, that also means I consider it fair game for your test for like a vocabulary matching definition question. Little hint. So a pure substance, when we're talking about a pure substance, we mean that the substance consists of only one type of matter. Only one type. And then last year you learned about elements. Elements from the periodic table of elements. This is a pure substance that you can't break down into simpler substances. So for example, you can, Riley, have pure water, no problem. But water can be broken down. Most of you know what's water's chemical formula. It's 2 hydrogens and 1 oxygen. You could break it down further into pure hydrogen and pure oxygen. Now you've broken it down into its elements. Okay? So just because a substance is pure doesn't mean it only has something on the periodic table. It could have a compound and be pure of that compound. Everybody get the hole puncher? There you go. Thank you, Maleva. Compound. A compound is a pure substance that's composed of 2 or more atoms combined in a specific way. Water, H2O. Sodium chloride. Sodium chloride was NaCl. Oh, that A shouldn't be capitalized. Hole punch it. Yep. Etc. Atom is the smallest part of an element. Right? So, Tim, hopefully most of this is somewhat review, but we're brushing the cobwebs off. We're writing down stuff, right? You with me? You zoned out for a second there. Come back. Okay, so find definitions. It's there somewhere. And molecule is the smallest part of a compound. Yep.
We don't even know what page we're supposed to be on.
Okay, can you help them out? Ask a neighbor. I should have turned page numbers on when I printed this, and I didn't. I will next time. Okay. So we're going to kind of go in order, but you got to keep on your toes. We're good? Okay. Molecule is the smallest part of a compound. So a water is a molecule, H2O. Element is broken down further. We're good? I think we're going over the next page now. Organization of the periodic table. So, here it is. Elements are listed by atomic number, not by atomic mass. So that number that you see in the top left corner, that goes in order, 1, 2, 3, 4, 5, 6, 7, etc. That's its atomic number. What else does that number tell you? So let's go find an element on your periodic table, which hopefully you kept in front of you, the pink one that I handed out. By the way, for the next while, probably first thing you want to do when you open your binder is also keep that pink periodic table handy. Get used to finding where stuff is. That's identical to the one on the provincial exam that you guys get. Eric, what I'm also trying to do is to get you to almost train your eyes to look in the right place so that you spend less time searching on the exam, because it's a timed exam, and any way I can save you time is a good thing. So all of you find element number, count them, 5. Boron. Okay? Element 5 is boron. What else does that 5 tell you? How many protons does boron have? 5. How many electrons does boron have normally when it's neutral before we muck around with it? 5. How many neutrons? Not necessarily 5. That number doesn't tell you that. That's the one kids get mixed up the most. They want 5 neutrons. Might, probably not, maybe, maybe not. Okay? So the atomic number tells you how many protons, how many electrons when neutral, and where it sits on the periodic table. Hey, what's atomic number 17? Fluoride? Chlorine. Sorry, chlorine. How many protons? 17. How many electrons when neutral? 17. How many neutrons? That's a different page. That's a different trick. So, here is the key idea. If there's one thing I want you to come out of this, the number of protons, which is also the atomic number, tells you what element we have. Let's suppose, let's go back to element number 5, boron. Let's suppose through some magical process we could force boron to accept 2 more protons. Would it be boron anymore? No, it would go from being element number 5 to element number 7, which is nitrogen. Can we do that, Mr. Dueck? That happens on the inside of stars all the time. Stars push down on their insides with so much gravity that they can literally fuse atoms together, and that's how we get bigger and bigger elements and bigger atoms. And we can also do it ourselves in particle smashers, particle colliders, like the Large Hadron Collider. That's some of what we do there. We smash them together at almost the speed of light, and we're hoping, if we're lucky, that 2 nucleus, rather than bouncing off of each other, will stick together, and suddenly we'll have more protons. That's how we've managed to build most of the elements on the periodic table past element 91. Everything up to element 91 or 92, I can't remember, exists in nature. Everything after that, we faked it. We created it. So key idea, number of protons is the atomic number, which is what determines the element. Why is that so important? Because when we look at radioactivity, that's going to change. This means that if you somehow gain or lose a proton, you become an entirely new element. I think there's a spot to fill that in, right? This happens inside stars, and we can recreate, Jared, some of those conditions in particle smashers and particle colliders. A row is also called a period. Now, a row is horizontal, not vertical. So the first period has 2 elements. The second period, the second row, has 8. The third period, the third row, has 8. The fourth period has 18. And then it goes a little weird and wonky. You may notice somewhere around element 57 on your periodic table that there's a line drawing to some below there, because then the periods get so big we can't fit them on one page. So it's traditional to say, rather than go crazy wide, well, those would squeeze in there if we could. We're not going to go that far down on the periodic table for the most part. Each column is called a group or a family. So the first column is part of a certain family. The second column, going to make it, Cody? You're looking pretty bad. Ah! Nothing? No? My aim was off. I hit Donna. And I'm sorry. I got to work on my aim a little bit better. But okay. Wait for it, though. Wait for it. You feel great now, though, don't you? Ah, I can wrestle a tiger. Ah, I'm awake. There you go. Get used to it. Did you even twitch, or are you used to it? Yeah, right? You had me. The kids that had me last year, like, whatever. So each column is called a group or a family. And if they're in the same column, that means they usually have similar characteristics or properties. Often they'll combine with the same other elements in the same ratio, often. Next page over, or next square over, or whatever, right? You with me now? Okay. I didn't number them, so you've reminded me. I'll see if I can put a little number thing on there next time. So for the periodic table, metals are on the left, non-metals are on the right, and there should be, if you look on your photocopy on your pink, a staircase line that separates them, yes? I tried to make this a good enough copy that you can see it. Turns out that's tougher to do than you realize on a photocopier. I had to hunt around for a periodic table that I could print properly. So metals on the left, non-metals on the right. How can I remember that? I'll be honest, I know enough metals that I can usually figure it out. So for example, I know iron is a metal. It's element number 26, and it's kind of on the left side of that staircase. So I usually clue, oh, those are the metals. I know that nitrogen is a gas. It's not a metal. So I know that the right-hand side is non-metals. Lots of information in each square. You need to know how to use it. So we're going to fill some of this stuff in. So I think I gave you iron on your chart, right? We're going to talk about what each one of these things means. So don't turn the page yet, or be on this page. So draw a little arrow pointing to that number. What does that tell you? That 26. Okay, first thing we can call that atomic. Are you guys okay? If I haven't told you yet, start learning to abbreviate in your notes. So my abbreviation for number is a number sign. What else does that number tell you? It tells you 2 things always and a 3rd thing usually. Give you a hint. Number of. Did I give you guys a good abbreviation for proton? Are you cluing in? Right? Can I go P+? You can write the word protons, knock yourselves out, but it's worth coming up with, especially if you're going to post-secondary, an abbreviation system that you understand, or otherwise your elbow will fall off from writing so much. So you'll write proton. But you won't be able to keep up. Most profs will just talk about at the same speed as you and I have a conversation, and they'll expect that you're writing it down, and most people can't write as fast as people can talk. So you come up with a system that's an abbreviation of some type. And I'll teach you a few of the tricks this year too. First one is you abbreviate number with that. There's one more thing. It tells you the number of electrons, but I'm going to put in brackets when neutral. It doesn't tell you the number of electrons if it's combining with other stuff. Remember the whole ionic bond, atoms share, swap electrons, all that stuff. So it changes. Okay. What about these two numbers in the top right? What do those tell you? Yeah. It's a word that begins with a V, and there's a candy, if anybody can remember what the word is that begins with a V. I heard it here. Sorry, what was it? Okay, this tells you the... spelled with an E, Mr. Dueck. The valence charge. Tells you the valence charge. So iron is multivalent because there's two numbers there. Multi means more than one possible valence charge, which also means it combines in different ways and it's tougher. Most of them, the nicer elements, the ones higher up on the, earlier on the periodic table, hopefully they're single valent and they're a little easier to deal with. But what this told you was ways that you could use, you may remember from last year, the Criss-Cross Rule. Okay? So what we're saying is iron, when it combines with stuff, either wants to get rid of 3 electrons and become positive 3 times, or it wants to get rid of 2 electrons and become positive twice. What was this? Symbol, abbreviation, but symbol is the fancy name. Mr. Dueck? Yes, Jared. Why isn't the symbol for iron IR? It's a good question. Why isn't the symbol for iron IR? Because not all scientists speak English. Yeah. In fact, a lot of the symbols are from Latin. A lot of the ones further down were discovered by countries, and so the people in that country may have named them after that country or a place in that country. That's why there's so many elements that begin with the letter Y and the letter T. There's a village in Sweden called Yttra, where they found a whole bunch of previously undiscovered elements in a mine. And so there's yttrium, there's ytterbium, there's a bunch all named after this place. Iron, name. And then the last one, that 55.8. What did we call that? Atomic mass. Mr. Dueck? Yeah. Why 55.8? Why not 56? Well, we rounded to 56. It turns out, don't write this down, but I'm a nerd, I have to tell you, that's actually the average atomic mass. Some atoms of iron weigh a bit more, some atoms of iron weigh a bit less, and that's where radioactivity comes in. Because when atoms are radioactive, one of the ways that they become radioactive is they don't get rid of protons, they don't get rid of electrons. Okay, what's left? They get rid of neutrons. And that changes their mass, because neutrons weigh about the same as a proton. Okay? All of you, for example, every time you eat a banana, there's a small percentage of the potassium atoms in a banana. Atom's a good source of potassium. There's a small percentage of those potassium atoms that are radioactive. All of you ingest radioactive stuff all the time. And our bodies deal with it pretty good. Preview of coming attractions when we get to radioactivity. Turn the page, or next slide over. I don't think I included this in yours, right? Periodic table. So you all got a copy, though. Again, for basically till about Christmas, when we sit down, get it out. Or you can impress me and memorize it. Put your pencils down, please. Periodic table of the elements song. I might show you that video in a second. Let's see. You know what? I think we might. So let's do this. Pause here for a second. All right, take a look at what I've given you. This is not all immediately due. I haven't covered it all yet. But first of all, the first thing I gave you is called Fun with the Periodic Table. These questions are horrible jokes. Horrible jokes. But this is also to kind of get you familiar with looking around on the periodic table. For example, what's the answer to number 12? Mickey Mouse loves this element. Which one? Really? I thought that one was an obvious one. Plutonium, because his dog is Pluto. They're terrible. To make you laugh, see if you can get some of these, and if you can't get them, I'm not going to freak out. What I do want you to practice is on the back page. Now, I haven't talked about this yet. This is a review from Science 9. What we're doing is we are counting the number of atoms in each chemical formula. And remember, to count, you had to be really, really careful with subscripts and how those worked. So, for example, we're going to do number 2 together. Okay? What does the letter K stand for, first of all? Potassium. How many potassiums are there in this particular formula? On the single page. Okay? On the back of the single page. Okay, Malib? Right? Yep, right here. So, looking at this, if we're counting how many different atoms there are, we would say there are 3 potassium. What's a capital letter P? From your periodic table, what's that one? And I know it's been a while, that's why I'm doing this, because this is going to force you to look at your table a whole bunch, and you'll start to memorize the important ones because you're naturally lazy. How many of those are there? 4. Is that 4 on the P, or is that 4 on the O? If I wanted it to also be on the P, what would I have done? It begins with letter B and rhymes with rackets. Okay, so remember how this all works? So there's going to be 1 phosphorus and how many oxygens? 4 oxygen. So Alex, what we're going to be doing is counting these, and you're going to get a lot of these wrong. That's okay, Dominic. Wake up, kiddo. We're trying to brush the cobwebs off. I'm okay with that. I'm not going to mark this out of a score. What I am going to do is go over the answers next class. So you want to think about how many N in number 3, how many N nitrogens there are. I'll give you a hint, more than one. Yep. Number 3. Okay, let's do number 3 together, and I'll let you try the next of them. How many N's are there in number 3? Not 1.
4.
I heard 4 and I heard 2. Which one's correct? First of all, there's a little number right here. It's invisible, but there's always an invisible 1 there. So how many are there now? You see it, Donna? What? 2. And what's N? Nitrogen? How many H's are there grand total? Not 4. Where'd the 8 come from? Right? This is sort of like, almost like FOIL in math. 8 hydrogens. Okay, we took care of the N's, we took care of the H's. What does S stand for? How many of them are there? Careful. Yes, 1 sulfur. How many oxygens? You're going to, especially because it's been a while since you've done the chemistry, you're going to struggle with this a bit. I'm okay with that because it'll help us identify for next class what I need to brush up and go over. And I'm going to be doing bonding and chemicals and formulas next class. So for next class, try this. Definitely do next class. And then if you finish this in class, this sheet that I gave you called Section 4.1 Homework, you can't do all of it, but you should be able to do the top half of the first page. You should be able to do number 1 and number 2, and you might be able to do number 3. So you can try that if you want, but otherwise you can also just bring that back, and next class we'll pick up with this. So for sure, try the single sheet for Wednesday and the other one.